Hello everyone. Welcome to this Sentinel Hub webinar. Today we'll present how Synergize and Sentinel Hub have contributed to the Horizon 2020 project NIVA, which aims to improve and digitize agricultural practices in Europe. And in particular, we will show you how you can use Sentinel Hub to build machine learning applications for large-scale usage. The presentation today will be given by our colleague Nate Vesil from our EO research team here at Synergize. And now I give the floor to Nate to start with the agenda.
Hi, everyone. I hope everybody hears me well. So as I was introduced already, my name is Nate Vesil, and I'm a member of the EO research team at Synergize. And today I'll be presenting the automated agricultural field delineation tool that we developed in the scope of the NIVA project. So first, a quick look at the agenda for today. So today's webinar is split into four main parts. The first part is what is field delineation tool and how it can help you. Then we will move on to the main part, so the overview of the technical components. We will take a look at the main steps of the field delineation process and how they are implemented in our tool. Then we will go to the hands-on demonstration of how the tool works and how it can be used. So we have an open source repository where all the code is published, and we also have an end-to-end notebook which everybody can run, and I will show you what needs to be done in order to run it. And then there will be a short section on discussion on possible future improvements in the tool. So going to the first item on the agenda, what is the delineation tool and how it can help you? So what it is, it's a tool for automated delineation of agricultural parcels based on Sentinel-2 images. And what's also important is that the source code with instructions on how to run it has been published on GitHub. So this tool has been developed by the EO research team at Synergize in the context of the NIVA Horizon 2020 project. And there the goal is kind of to use Sentinel-2 imagery, more specifically the 10-meter optical bands, to delineate agricultural parcels. This is done by training a supervised deep learning model, more specifically the ResUnet-A model. And of course, if you're doing any kind of deep learning, you need some kind of source imagery or training data. And in this case, this is the GSAA vectors. Yeah, GSAA vectors or any other kind of delineated fields as input to the training model. So why is this important? In the scope of the Common Agriculture Policy, having accurate and up-to-date fields is very important because any kind of decisions or compliance checks you want to do on your parcels require that your boundaries are up to date and reflect what is actually happening on the field. And also in some places, there is no available information about the parcel boundaries. And having this tool can give you a nice approximation or a first step that you can then use to get this data. So having the results of this tool, you can identify wrongly delineated parcels, but it also gives you an option to run object-based algorithms such as crop detection without having a priori parcel boundaries available. Now we're going to the main part of the presentation, which is the overview of the technical components. First, let's take a look at the main tools that are utilized by our tool. So we rely heavily on the Sentinel Hub large-scale batch processing API for downloading the Sentinel-2 data. And because this downloads data asynchronously to the AWS bucket, we also rely on AWS 3 for storage. So this stores the data that we produce within this workflow. We are also using or relying on our EOLearn and EOFlow open source frameworks that we developed in-house and are kind of very reliant on them in our work. And we use TensorFlow for training and the inference. In addition, our workflow also uses some other technologies that are kind of well known, such as we rely on a Postgre database, and we use GDAL for the post-processing purposes, as I will explain later. So the workflow itself can be split into 10 main parts, which are the data download. So this is where the Sentinel-2 data is downloaded using the Sentinel Hub service to the bucket. Then we go from the downloaded geotiffs into EOPatches, to which we add kind of reference data, so the GSAA vectors. Then from these big patches, we use sampling to sample smaller patchlets, which are then converted to a training-ready format that can be then input into the training of the model. Of course, with any kind of machine learning based on images, we need to take care of the normalization. So there's a step that calculates the normalization factors and saves them. And we also do k-fold split before we do the training of the model. After the prediction part, the predicted kind of field boundaries need to be post-processed, and the post-processed rasters are then vectorized to obtain the final result. So at the end, so you go from having an area of interest to the vectors over that area of interest within this tool. So the first step is the download of the data. And here we heavily utilize the Sentinel Hub Patch API. So the data is downloaded asynchronously to the S3 bucket. And we are using the Sentinel Hub Patch API because it's fast. So for example, we download the data across the whole Lithuania, and the data was downloaded in less than 30 minutes for basically a year worth of data. And when we do this process, we download basically all the 10-meter bands, so RGB and near infrared. And we also download the cloud probability band. This is something that's also available on Sentinel Hub. And it's a cloud mask that's been produced by our S2 cloudless cloud detection algorithm. Of course, the time interval of the downloaded data can be arbitrarily set, but if your goal is delineation of boundaries, this usually covers the growing period when fields are not bare. But of course, if the use case is a bit different, this can be changed. When you are using Batch API for the download of the data, your area of interest is split into a predefined grid. And in this case, we use the 10-kilometer overlapping UTM grid. So each cell of the grid is a 10 by 10 geotiff that will be stored to the bucket. It's also important that this grid is a bit overlapping, because at the end, when you are kind of trying to merge results into a wall-to-wall map of vectors, you need some overlaps so that you can do seamless merging. And of course, I mean, this data download part is important, but if you already have data available, this can be to some degree skipped. So because Batch API downloads the data in the form of geotiffs, but we find it easier to work with EOPatches because we can store all the data all the data that is associated with that area into the EOPatch, so the bands, the raster masks, the vector data, and so on. That's why we need to do first the conversion of geotiffs that are the resulting of the Batch API into EOPatches. And then we need to import the vector reference data to those EOPatches. And to do that, the vectors need to be stored in a PostGIS database and are then imported using a task from EOLearn. Once the vector data has been imported to the EOPatch, it is then rasterized to 10-meter resolution. And in our use case, a negative buffer of 10 meters is applied to try to align the GSAA data with the Sentinel-2 pixels. So the model is not taught boundaries that are sub-pixel and can't be seen. But of course, this is another thing that is quite configurable. So the logic here is that if you have some very small boundaries, some very small fields, and you rasterize them and you don't apply negative buffer, you might show the model boundaries that it cannot see due to the limitation of the resolution. And that's why this part is done. The model that we use requires us to compute 3 different masks from the vectors. And this is the extent mask, the boundary mask, which only kind of rasterizes the boundaries of the fields. But we also create a distance mask, which for each pixel that is contained within a parcel, it assigns a value that means what the distance of that pixel is to the edge of the parcel. And this is kind of due to the way that our model is structured. In the sampling step, so once you have the EOPatches, the next step is sampling. So in the sampling step, smaller patchlets are sampled from these EOPatches. And this is done so that the kind of the following steps that come after this are easier on the memory. And it's one step closer to what the model actually expects. Using sampling, a constraint can be made on what exactly is sampled. Basically, what we can do is, if you just sample without any constraints, it can be that a lot of patchlets contain no reference data, and this can make it hard for the model to learn the actual boundaries. So you can make a constraint that each sample contains at least some percentage of reference data, and this helps the model when you're doing the training. And you can also make some constraints on the amount of cloudy or invalid data that you allow into the samples. The goal here is to have the samples be as clean as possible so that the model sees only clean and nice data. Again, the cloud coverage is determined by the cloud probability layer that we downloaded in the download step. And basically, you can impose some restrictions on how many pixels within your sample need to be cloud-free in order that the sample will be accepted. Again, you can also choose to sample only negative samples if you're having trouble with the delineation of areas that are not agricultural land or so on. And we see that together with the actual bands, we also sample the reference data. So again, all the data that is associated with an area of interest is then converted into a smaller patchlet. Because of memory limitations, and because we cannot fit the whole data set over a whole country, for example, into memory, the sampled patchlets are chunked and stored into multiple MPZ files that allows us to efficiently access the data during training. To do this, we rely on the data loaders and on kind of utilities that are available in our open source EOFlow framework that kind of builds on top of EOLearn to move further towards support for deep learning. And in each of the MPZ files, we store keys for features, labels, timestamps, and name of the patchlet from which it was taken. And you can imagine that each timestamp of the sampled observation is its own row in one of the MPZ files. And to make further processing of these MPZ files easier, we also create a pandas data frame which tracks the contents of these MPZ files and allows us to do filtering and to see where our data is coming from and so on. After we have the data in these MPZ files, it's also important that we take care of the normalization before we do any of the training. And here the idea is that we want our model to perform well over timestamps taken over the whole year, so regardless of the time. So it's very important how the data itself is normalized. If you look at here at two examples, so here is some satellite imagery over an area that was taken at end of April. And here is some imagery that was taken beginning of June, and you see that it's quite different. And also here, if you look at the distribution, so this is the distribution of the first one and the distribution of the second one, it is quite clear that the distributions or the histograms are different. So the normalization for these two also needs to take this into account. So we compute normalization statistics on a monthly basis. What this means is that we look at observations in a certain month and calculate certain statistics on those. So the statistics that we compute within the tool or within the workflow are various percentiles. We compute the mean, we compute the median, and we compute also the standard deviation. And then during the training, you can basically write your own, or you can use one of the predefined mean standard kind of normalization techniques, or you can use the statistics computed and do your own normalization in a way that you want or that suits your use case. Because you want results for the whole area of interest, doing train test validation split, which is kind of one of the standard ways in machine learning, is not feasible because you can't afford to reserve some part of area just for validation or just for test. So we split the data into folds, so we can do prediction over the whole area of interest. But there's a bit of limitations here. So because small patchlets that we produced can be sampled from the same EOPatches and can overlap, this split of the data has to be performed on the EOPatch level. And additionally, all timestamps of a patchlet need to belong to the same split. And again, the number of folds that you have is configurable and can be changed according to your wishes, I guess. So the model itself is a ResUnet model based on a paper made by Waldner et al. Here is also a link shared. And it builds on top of a UNet architecture, which it expands with various different elements. So one of these is the conditioned multitask output, which is this distance at extent and boundary outputs. Then we have the residual convolutional block. And we also have the pyramidal pooling module, which tries to add global context by combining features pulled at very different scales. The model itself is implemented in our EOFlow tool, and it's available also if you want to use it for any other application. And we train K models, one for each left-out fold. And at the end, we average the weights of these K-fold models to create a single model. We realized that this is slight cheating because you are predicting not something that one of the models that was used for the average model has seen. But if using a sufficient number of folds, I guess the cheating is minimized in this case. This is done mostly because we want to have a model that is consistent across the whole area of interest. So to minimize the border effects that might be there if you have different models that learn slightly different things across different EOPatches. It's also important to know that the model learns to predict all three maps. So it learns to predict extent, boundary, and distance. And for each, when we're doing inference, we get all three. And prediction is single temporal. So this is a single temporal model. So when doing prediction, it's done for each available acquisition. As I said, prediction is performed over EOPatches. So we trained the model on smaller patchlets that by default are 256 by 256 in size, but prediction is done on whole EOPatches. And if you use the default settings that we have in the notebooks and in the repository, these are around 1000 by 1000 pixels. And we only do prediction on cloudless timestamps. So we look at the time, all the acquisitions within an EOPatch. So here you can imagine here a temporal stack of predictions. And we filter out the ones that are cloudy. So I think the default limit is the ones that contain more than 5% of clouds are disregarded. But there's also an option, I think, that the prediction is done on all, but it's not. But the cloudy pixels are disregarded when doing the temporal merging in the post-processing. And again, yeah, the prediction done is single temporal. Once you have kind of the predictions, it's not the end of the story because there's some other things that are involved that are quite important. So, for example, we do post-processings. So predictions are, so like I said, we do predictions over multiple timestamps. And then these timestamps are temporally merged over a specified time interval. This time interval can be whatever you want, so it's configurable, but we've noticed best results by using monthly or maybe quarterly time interval. So you take a time interval, which is where the fields are best or where they are most representative of what you want them to be. So this is usually late spring or early summer. If your use case is agricultural parcels delineation, and then you combine them, then you temporarily merge them by by using kind of median across the temporal dimension. Here it's also possible to use other statistics, so it's not necessary to use median merging. You can do some other percentile, and we leave this kind of as a configurable option in the tool. After the temporal merging is done, we need to combine the extent and boundary probabilities. So currently in our post-processing, the distance that is also predicted by the model is not used, and we use only the extent and the boundary. And what we do is you take the pseudo probabilities returned by the extent and then add one, and then they kind of do the difference with the boundary. So this tries to mimic kind of the difference operation that you would do if these were simple sets. So if this was a mask itself. So here the idea is to only predict, to have kind of clear distinction between neighboring fields. So that's why this is done in such a way. After you have this mask, so the one returned by the extent and by combining extent and boundary, the last step is the vectorization. So what we want out of this is not actually a raster image. We want a vector image, and this is also, we want vectors that we can use in our favorite GIS tool. So what is done? The resulting rasters from the previous steps are upscaled, and they are smoothed and combined into a virtual raster. The values over the overlap, like I said, we have overlapping EOPatches, are then graduated to make a seamless transitions from the pseudo probabilities obtained from one patch into another. So what we want to avoid are the border effects. Here we utilize the virtual raster functionality that allows us to define a function over the overlap. And after we have this, we use the Dihedral contour utility to get smooth vectors out of these pseudo probabilities that are defined in the virtual rasters. However, this last step is a bit tricky because you cannot do contouring over large areas. So, for example, if you have your area covers the whole country, it will be too slow or it won't even run. So what we need to do, we need to split this combined virtual raster into smaller chunks, and then calculate the contouring, and then join these contoured results back together with the unary union operation. However, doing this efficiently and in a way that works fast enough over large areas is quite tricky. So we built an algorithm to do this. There's a workflow included that does this over large areas in a quite efficient manner. And after we have this, so all of this is done across a UTM zone. And if you have a very large area of interest, it can happen that it spans multiple UTM zones. And so there's a last step of the process, which is maybe needed, maybe not, depending on your AOI. And this is the UTM merging. So in the previous step, you obtain two GeoPackage files, or multiple GeoPackage files for each UTM zone, and then you need to merge them together into a single GeoPackage that covers your whole area of interest. So this is kind of the whole procedure from end to end. I hope so, kind of an overview of all the main steps. And now I will show you the notebook that we prepared. So the end-to-end notebook that you can use to run this whole thing from beginning to the end. So first of all, this code is freely available on our GitHub page, on the field delineation GitHub page. And in the following slides, there will also be a link to that. To install this tool, it's quite simple. So what you have to do is clone it locally or to a machine, and then run the setup in Python. So this fully runs in Python. And then you can get started with the end-to-end notebook that I will show you now. The end-to-end notebook basically is a notebook that goes through the whole process that I just described with minimal input required, with minimal work required by the user. Of course, if somebody wishes to change something or so on, or to improve something, We also accept pull requests and would be very happy to do so. This notebook includes the training and prediction using a neural network. So if running over larger areas, we recommend using a machine with the GPU setup. And to run this notebook out of the box as it is, access to AWS S3 bucket is required, and also the Sentinel Hub credentials are required for the download of the data. But other than this, basically the only two requirements that are needed are the georeference file with the area of interest and the field boundary ground truth data for training. And as you can see, the first kind of step is the setup of the credentials. Here, just set up your bucket, your AWS credentials, and the Sentinel Hub client ID and the secrets. Then you need to set up the project data root. So this is just a local folder where all the project-related files are either already stored or will be stored. And then you need the AOI GeoJSON. So this is a GeoJSON which contains the boundaries of your area of interest. And you need to define the time interval for which the data will be downloaded. And then you can go basically through the notebook, and you need to set some other things. So for example, you set the location on the bucket where the TIFF images will be stored. And you can also basically configure the process through these configs files that are scattered through the notebook. So here, most of it is already set, but you can control the grid that you use for the download with the batch API. You can control the bands that you download. You can control the Sentinel-2 scenes, so the max CC, and you can control the mosaic in order. Once you have this set up, you just run the batch download function, which downloads all the data into the S3 bucket. Once this is downloaded, you can do some sanity checks. So you take a look at the grid that was returned, and you can plot it, and so on. So after you have the GeoTIFFs that were downloaded to the bucket, you want to convert them to EOPatches. And again, you just specify the location on the bucket to which EOPatches will be saved. And you specified some kind of the name of the features of the EOPatch here, just so that it's consistent with what you want. But in this case, I would suggest that most of the things are left the same. So again, just call the function, and then you do some sanity checks on what data has been returned. So here you see that our area of interest is covered by a grid of 6 GeoTIFFs or 6 EOPatches. And here we see that the resulting area is made of 6 smaller of 6 EOPatches were created. And then we can load an EOPatch and just plot it to see that everything is as we expect it to be. This is the only step in the notebook that is a bit trickier, and it requires some maybe extra work outside of the notebook. So here, basically, because of usually the GSAA files over large areas of interest are quite big, the best solution to import the vector files into the EOPatches is to ingest the reference data or the vectors into a PostGIS database, and then use an EO task that has been prepared to import the data correctly. So here you have the full. So even though this looks a bit daunting, it should run out of the box. So there's a script that tells you how to run this. All you need to do is change the name of the files that you are importing correctly, and then the following steps should work out of the box. Again, there's a lot of options for configuration. So you can choose the negative buffer that I talked about. You can choose the smoothing of the cloud masks and so on. Another thing to note, maybe here already, is that most of these kind of workflows or processes support multiprocessing. So this max workers parameter takes care that if you're on a machine with multiple cores, you can parallelize, and everything is done faster than on one single core. And again, the same as in the previous steps, you run it with the function, and then you look at the results and just to check that everything has finished as you expect it to finish. After having the patchlets ready, the patches ready, we move on to the sampling. And again, you specify the location on the bucket to which sample patchlets will be saved. And again, we have options to configure what exactly is sampled. So we can configure the buffer, which means we do not want to sample over the overlap because, again, we don't want to cheat. So you have an option to configure that, and you have an option to configure the size of the patchlets that will be sampled, the number of samples, the fractions of valid data that needs to be in the sample, and so on, and the cloud coverage limitation. Again, also the max workers. So this should all run kind of out of the box in this way. Again, once you have this, you run it, you check what is on the bucket, just as a sanity check that everything finished as you want it to be. After having the samples, we calculate the MPZ files, and again, specify the location on the bucket to which they are saved, and we specify the paths to the metadata data frame. So the file path to which the metadata data frame will be saved. And this needs to be a CSV file. Again, when we are doing so, when we have patchlets and then we chunk them together into MPZ files, we have an option to specify how many kind of samples will be in each chunk, and this parameter controls for that. And again, after running this, we check what was performed to see that if everything makes sense. And we also here check that how the data frame looks, and you see that there's a name of the chunk, the EOPatch from which this element came from, the patchlet from which it came from, and the position within the chunk. After we have the MPZ files, we do the normalization statistics. And again, we compute them and we save them into the data frame. Then we do the k-fold cross-validation. Again, this step loads data frame with the patchlets. So this one that was done in the previous step, it splits the EOPatches into k-folds and updates the info CSV with all the information. And again, of course, we also set a seed here so that because this is done randomly, we want it to be reproducible. Again, some sanity checks just to see that everything that was performed makes sense. Here we come to the training, and here we also specify some other things. We specify the local folder, model folder, so the local path to the folder where the models are saved. We specified the S3 folder where the models are saved, and we can also specify checkpoint folder. So this means that if you have a pre-trained model, or if you trained the model before and you want to train it more, you set this option. And again, there's a lot of things that can be adjusted and tweaked here, and I won't go into too much detail, but it's basically the things that one would expect doing model training. So you can change the batch size, the iterations per epoch, the number of epochs. You can configure the model in any way you wish, and so on. Yeah, once the model is saved, we check if it's present and we load it. For prediction, basically same story. You have a configuration file that you can configure with certain parameters that, yeah, again, and once you run the prediction, the predictions will be added to the EOPatches. So this is the input, and then for one of these, you see the extent and the boundary mask that were predicted by the model. And here it's the same visualization, just zoomed in a bit more, just so it can be more clearly seen. Please note that this is an example model, so it's not representative of the actual quality of what is returned. And then second to last step, predictions for each timestamp are saved to EOPatches. We temporarily merge them. So in this step, the following is executed. So you merge predictions over a time interval using percentile statistics. You join the extent and boundary predictions derived in the previous step. And you iteratively also smooth and upscale the joint predictions for a visually smoother output. And you export the resulting map as a TIFF to be used for vectorization. Again, specify the raster results folder, so the location on the bucket to which the EOPatch T files are saved. And then we have some configurations. Here we specify what the one that we expect that people will change the most is this time interval. So you specify the time interval over which you want to temporally merge your predictions. And again, this is just done by a dictionary. It is totally dependent on the use case. Whatever your use case, you need to change this. And again, some other configurations that can be adjusted based on the needs. Once the rasters have been kind of post-processed and exported, there is the vectorization part. Here we specify which time intervals we use. So this part here needs to match what was done in the previous step. And we specify also the UTM zones that are within the area of interest. So in this case, in this small example, there is only one UTM zone. So there is only one element. Here is the shape of the raster files that are exported. And there are also some configurations for the vectorization part, which we suggest probably to initially leave as they are and only change if something is not working as expected. And yeah, now we actually come to the final output. So once the things have been vectorized, you can load it with the GeoPandas data frame, and you can visualize the results either here or you can use it in your favorite GIS tool. There is one last step, but it's only partially needed. It depends on how big your area of interest is. And this step is the merging of the UTM zones. And again, here you specify the time interval as before, and you specify the UTM zones from which your area of interest covers. So in this example, when I was running this, I had a very small area of interest. And of course, you need to choose an appropriate meter-based CRS that covers your area of interest. Other than the merging of the UTM zone, there's some cleanup. So it can happen that your model doesn't or delineates certain big areas, such as lakes or so on, as a field. And you can set a criteria that big polygons, too big polygons will be thrown out. But again, this is completely configurable and you can remove it. And yeah, this is it regarding the notebook. And there's only the last part, which is a small discussion on possible improvements. As I said, in a way, this tool is based on what we needed. So our use case was delineation of agricultural parcels on Sentinel-2 imagery. But it is built in such a way that a lot of things are configurable, and certain things don't need to. If you have a different use case or something like this, you can change it. So one of the things that could potentially be changed is the input data. So rather than the download step, there is nothing hard-coded that would suggest that this needs to be Sentinel-2. And it also doesn't need to be at 10-meter resolution. It could potentially be at something lower resolution. Of course, you can always tweak the model. The model is based on the paper by Wagner, and we found it useful. But if somebody wants to play around and try a different model, of course, it's possible to add it. And of course, there is a lot of room to play around with the temporal merging. So like I said, we use median statistics for the temporal merging, but one could potentially use any kind of percentile. One could play around with different ways of combining probabilities. And again, you can use the different vectorization. So we use Dihedral contouring, but there are other options that could potentially be used. So what we tried to do is have a framework that works out of the box for certain things, but can be quite easily adjusted with some modifications to the code that are more software-based and do not conceptually change the workflow as much. Yeah, that's actually from my side, covers about everything. So I guess now is the time for the questions and answers, where my colleagues will answer some questions that were already opened.
Thank you, Nate, for this. I can use Simon's comment for excellent overview and demonstration. So let us proceed with your questions, like you said. I can mention also that beside Nate's, we have also Davis, Matej, and Anne today with us, so they will help us answering. So let's continue with the first question already asked in the chat. Catherine was asking, what's the exact name of the cloud detection algorithm?
Yes, hi everyone. So the cloud detection algorithm is published on GitHub under GitHub Sentinel Hub. It's called S2 Cloudless and works on S2 data, Sentinel-2 data, level 1C.
Philippe was asking what is the minimum parcels area that can be detected. I believe Davis can answer.
Yes, hello everyone. So we've trained this on Lithuania and tested on different European countries where actually there are many small fields, but we didn't sort of determine or filter the size, the parcels based on the size, as we found that actually the determining factor is sort of the smaller dimension of the parcel. So you can have a parcel with quite large area, but being very elongated with the smaller dimension covering only 1 or 2 Sentinel-2 pixels. So sort of that's the limiting factor. And you will see this when you rasterize your vectors to the grid at 10-meter resolution. So basically you will see that these vectors don't get rasterized, or you will only get 1 pixel out, and this is really difficult sort of to be predicted by the model. So sort of rather than the area of the parcel, you should be looking at the minimum size of your parcels, which typically have a rectangular shape.
Ellen was asking if you download data across the season and sample from EOPatches and image, you have, say, 20 images for the one particular EO. So some EO images of the EOPatch have clouds, others not. So how do you sample for, say, a particular EOPatch in this case?
So during the sampling, one of the things that you can do, or we do, is actually limit or filter the samples that we have on the cloud coverage as well. So using that, you don't take into account the samples that have that are completely covered with the clouds. We limit these quite severely because clouds, of course, influence the predictions. So yeah, that's pretty much it. So the smaller samples we have are filtered based on the cloud probabilities that we get from the cloud masks to get into the samples the data where the clouds are not there, because the clouds are then also removed from the predictions during this temporal merging, where actually the delineated boundaries that would stem from cloudy images are diminished because of the temporal merging.
Thank you, Matej. I will keep you for the next one online as well. So Marcel was asking, is it also possible to use other data sources like aerial images or very high resolution data with the same tooling?
Yeah, I think Nate has already pointed to this in the last slide. Yes, absolutely. I think that's a good thing to try or do if you have the access to other data, either very high resolution data or maybe orthophoto imagery of your country. Of course, it is possible. And actually, with the tooling that is provided with EOLearn that actually already supports stuff like that, you can get the data either through Sentinel Hub, or you can load the data from your existing WMS services or existing TIFF files that you have. So yes, in principle, the whole pipeline should be the same, just different input sources.
The next question comes from Simon. With that K-folds design, what's the minimum number of EOPatches needed? This could make it difficult to train a model or a smaller area hittings.
It really depends. So in our case, the EOPatches are quite large. So they're like 10,000 meters, so pixel size 1,000 by 1,000. And actually we sample from these EOPatches smaller patchlets, which is what the model sees. And this is what's actually relevant. So one patchlet is one sample. So the more useful number is sort of how many samples you can get from an EOPatch. And this is what sort of you consider when training the model, whether you have enough samples or not. And this then is linked to sort of how many folds you can use. In general, I don't have a specific number. It really depends on the quality of the labels as well, and how large your area is, so the variability in your data. But what we have tried to do is to make this flexible and generalizable so that you can specify the number of folds, so the K, that you want your data set to be split over. And this is a function then of the number of EOPatches. So for instance, if you have a low number of EOPatches, you can reduce the number of folds and vice versa.
Vivek was asking how well would this methodology work in a smallholder farming settings, say in Sub-Saharan Africa?
I think it was Simon already in the chat that pointed to a work done by Sherry Wang and Francois. So kind of similar continuation of the work that we've used. So that's one thing, right? So when you're looking for very small farms, then you should go to the higher resolution data. Of course, limits given by Sentinel-2, as Davis has explained, they do limit or impose a limit on the size of the farm you can detect. That being said, even in Europe, smallholder farming settings are not uncommon. So in Slovenia, for instance, we do have a lot of very small parcels and we can still do something with Sentinel-2. So what I would suggest is, yeah, you have a look, right? If you can do something with Sentinel-2, perfect, because it's free. Otherwise, you have to kind of extend what you're after with high resolution data. That being said, if we move to the Sub-Saharan Africa, again, the field delineation as presented here is so the model is susceptible to the differences between fields, between agricultural, non-agricultural land. I'm tempted to say it's a glorified edge detector, which is not, but still, it does delineate changes that it can see from the input data in terms of mostly vegetation. So if you were to delineate fields that have very low differences from field to other field or non-field, then you're in problem. And having really good reference data to train on becomes more and more important.
Simon was wondering if you can explain more about voiding border effects. In particular, what is the function for the overlap area?
What we do is on the overlap, we basically construct a weighted average of the predictions, and the formula that we use there is just linear. So going from the overlap on one side of the patchlet, overlap on one side of the patchlet to the edge of the patchlet, going from 1 to 0. And then when you combine several patches like this, you end up at the border of the two patches. You get half prediction from one and half from the other. And if you're on the corner of 4, then each of the 4 contribute 1/4 of the prediction.
From Samuel and Simon, we got quite related questions, so maybe we can tackle these two together. So Samuel was asking how generalizable this is, and if he's training on mainland Europe and then run over the UK, should he expect accurate field boundaries? And the second question from Simon was about transfer learning, more on temporally and spatially basis.
Yeah, so we did a few experiments to see how the model actually generalizes, so both across spatially and in time as asked. And we've seen actually that the model generalizes well within Europe and also in areas with same latitude. So we did some experiments, for instance, in Canada, and we've seen that the model could basically be used without any fine-tuning. So we've done basically 2 different approaches. So one is taking the model trained, in this case for Lithuania, with the normalization factors for Lithuania, and apply it directly to a new area. And this sort of works well for neighboring areas, sort of with very similar, basically phenotypes or how the parcels look like. Otherwise, we've also tried for instance, using the same model in areas slightly different, like in Spain, so different type of soil and, of course, weather. And in this case, we computed the normalization factors for the new area and applied these to the data so that we kind of center the distributions, even though the overall distributions over the month are different. And we've seen it work quite well. And also comparing these to fine-tuning in areas where this sort of doesn't hold anymore, then we can take the model trained in Lithuania, fine-tune it on a small set of labels for the new area, for instance, Spain or some other more southern country. And this basically allows to transfer the model so that the boundaries remain the same. You just try to adapt the distributions to the new area. And we've seen that this works quite well. We also did some tests, for instance, in Australia, where again, the boundaries are picked up. So then you're trying to fine tune the model to learn different distributions against over the month or sort of possibly the shapes of the parcels, which can be different.
We got another question. If we have a code in R language?
So no, the code is in Python, unfortunately.
Simon was asking, how can we request access to GSAA data and on a country-by-country basis?
So again, yeah, so GSAA data, at least in Europe, according to the Common Agricultural Policy, should be kind of made available to everybody, so should be made public. Maybe not GSAA data, but some sort of data over the geometries of the fields. But that really depends on the country, on each country, and there's quite a lot of work already being done to harmonize this. And one such, hopefully, useful foray into harmonization of this is Euro data crops, which should come out in let's say a few weeks.
Alan was asking if it's possible to download the data not using the Sentinel Hub batch API, but the exploration or basic API. So she explained that she signed up for a trial period, but never used it, and it expired. So this is why the question is here.
Thanks for the question, Alan. So yes, we use batch API because it's much simpler and accommodating to very large areas. But the same should be possible or is possible to do with the process API. And luckily, the notebook itself relies on EOLearn, where all the tooling to use process API instead of batch API is already provided. So just instead of using batch API requests, there is Sentinel Hub input tasks. And once you create your own grid of EOPatches, you have EO executor and EO workflows to help you with that. And there are quite a few examples in EOLearn that already show you how you can do approach with process API.
Can the model around data storage be tweaked using other cloud storage instead of AWS?
Yes. So again, this relies on EOLearn. So in EOLearn, we facilitate either you have your own local storage or AWS. We never had any particular interest in trying for something different because this works for us. But in principle, yes. So you can run it locally. We did run successfully EOLearn jobs on EuroDataCube and some other providers instead of AWS, but typically we were using then local disks of the machinery that there is where the workflows were run.
So will the field delineation be available as a library or API call with your trained model, meaning can the user get the field delineations for an image in a bounding box calling a library or API?
Not at the moment. So having something like this, we would have to either limit the area of interest to where we think that our model generalizes well. And this is not yet, let's say, not quite an unexplored territory. So far, we have tried at some areas and it worked substantially well. So what we do for clients, let's say, if they have interest in this, I would suggest you get in contact with us, and we can try and come up with something that would work for you. But generic API call to get delineated fields anywhere in the world is currently a little bit out of scope, let's say.
After training and testing the model, how could we use it to predict new Sentinel-2 images?
Yeah, so basically you could use the same notebook that Nate showed. You just have to keep the steps where basically you ingest the GSAA data and run the sampling and so on. So actually what you need to do, so you download the area, so you won't have the GSAA data, put it in the EOPatches, and then you skip directly to the prediction step. So assume you have already a model. And then you can directly run from there onwards the prediction, the post-processing, and the vectorization. So this is what we did to test the model from, for instance, Lithuania to other areas where we possibly didn't have the GSA.
Davis, I will ask you also for the next one. Do you have any accuracy figures for your boundary detection results? And how about tramlines being misclassified as boundaries? Can we have access to, can the user have access to our trained deep learning model?
So regarding the first questions, I would refer you to the blog post that we wrote about this, where we also evaluate different sort of architectures building up to the res unit, and you will find numbers for the MCC score for the extend and the boundary. So for the extend MCC, for instance, we achieved around 75, 0.76, which is sort of a good indicator of a good agreement between the predicted extent and sort of ground truth as such. So we were sort of, again, happy with this performance. But again, you could see, maybe referring to the previous one, how this refers to the size of your parcel. So of course, you would get better predictions for larger parcels than the smaller ones. We cannot share directly the deep learning model, as sort of this is related to the GSAA and sort of the work we've done for this project. But if you're interested, you can contact us. We see, for instance, for different areas where we could share the data, if this would be possible or not. As for the tramline, we actually didn't notice any of this confusion in sort of our data sets, both in Lithuania and different parts of Europe.
The next question, maybe also for you, Davis. Is it better to use customized NN instead pre-training NN models?
I assume here as pre-trained models, you refer to sort of on natural images, so sort of resonets that you can find online. So we didn't kind of use this, but probably maybe even with the slight changes in the architectures, you might be able to use these pre-trained weights, which might speed up sort of the convergence to something. So we find otherwise that training from scratch your network, if the quality of the labels is good and actually you have sort of enough samples to capture the variability, is good enough, sort of gives you a good model by itself without the need to use pre-trained models in this case. If, as mentioned before, if you're fine-tuning to the different area, definitely it helps to have already a trained model, even if it's in a different area or different years. So for instance, maybe didn't mention this, we also try in the same model in the same area for different years, and actually we've seen it generalizes very well because the normalization factors are very similar between years, and sort of the labels are the same. So this is also a good generalization, better than sort of spatially to different areas.
Can you also tell us a little bit more about our experience with heterogeneous fields?
Yes, so this I think is where the model, sort of the complexity of the model kicks in, as this is actually not a simple just edge detector or sort of boundary detector. So as long as your training samples or training data set sort of capture this and is sort of consistent in labeling this, the model is able to tell apart sort of inhomogeneities from boundaries. So you can have, especially early in the season, or like in Europe, March or April, a lot of different sort of spotted vegetation or whatnot. So the model learns to basically ignore these differences as not as boundaries between fields. So this is all again in the training data that you provide and in the consistency in labeling this. So it's able to deal with inhomogeneities by itself, let's say, with the right training data.
Will the vectorized polygon include holes?
Yeah, so this is connected to the previous question, right? The heterogeneousness of the fields, and yes, we have had holes already where I don't know, a tree that, or a few trees, or a cove that was in the field was delineated out of the field. So yes, but again, this depends a little bit on post-processing as well.
Muhammad is also asking, is there any size for the boundaries to download data for area of interest, and how do you merge scenes or for scenes using Sentinel Hub?
Yeah, okay, very good question. Yeah, so the process API has limitations on when you request the data, and this is 2500 times 2500 pixels. The merging of the four scenes, let's say, using Sentinel Hub is possible, particularly if you're using, as mentioned here, EOLearn, or even Sentinel Hub Pi, which is a Python wrapper to the Sentinel Hub services. There are some functionalities where you can then split a much larger area into smaller areas and download everything for a smaller area. And the last steps in the process shown in the notebook by Nate actually also show you how this merging over EOPatches work to basically produce a wall-to-wall clean results.
The next question comes from Dokali. What level of Sentinel-2 images are used, L2A or L1C?
So in our process, we use L1C, but again, as was discussed a few times already, one can in theory use whatever. So either L2A or you can use even any other data sources.
So are there any pre-trained models available, I guess, for users to use them?
I can answer that. So unfortunately, what has been shown even in the blog post comes from Lithuania, where the GSAA data that we got was given to us by a client. So we cannot actually release the model itself. That being said, if you have a need for something like that, you can again contact us and we can see what we can come up with together.
Christian asked if we are ignoring cloudy pixels when computing the loss function.
So in theory not, but in practice, I guess yes, because we make sure that the data that's coming in to train the model is cloud-free. So we impose quite harsh restrictions on the cloud probability of our samples, so that our samples are in theory as cloud-free as possible.
Sumesh was explaining that most of the time they encounter features like trees, water channels, and similar along the edges and inside the farm. And these features can impact the model training and performance. Can you suggest an approach that can be used to overcome this?
I'm not sure. I mean, we didn't notice many problems related to this actually, but off the top of my head, I would say that one of the approaches would be, it all starts with the reference data. So it's either you try to, when you're rasterizing the data, you can try to apply a bit of a negative buffer, or if this is really problematic, you also try to kind of align your reference data to what you need as much as possible. Another option would be to manually find such examples and try to feed more of them to the model so that the model kind of learns what is needed. But as I said, this is a bit of a guesswork because we haven't noticed such apparent problems.
Did you apply any data augmentation techniques such as Dihedral or Color Jitter?
No. So the data augmentation that we use here is just basic rotation, I think, and flipping. So other than that, nothing. But I guess in the notebook, one could add their own data augmentation without any problems.
What is the importance of distance mask in the delineation task?
So I guess this is this was the distant mask was taken from the paper. And I guess the idea is also for one additional input to the model that tries to make a feed so that when the model predicts fields, it tries to be as consistent and have the boundaries as consistent as possible.
Is the processing done on AWS or locally on local machine? And how can one save download data and products locally to avoid paying for the AWS services?
So the processing itself is actually done locally. So except for the data download, the only thing that is done in AWS is the storage of the data. Out of the box, this is done in a way that kind of relies on AWS storage, but with a little bit of tweaking of the code. And I really estimate that this is not much. One could, without a problem, save all the data locally or on some local storage that is not AWS and run the process from beginning to the end.
Then we have another question from Ralph. He said that from this detection, one can detect really field delineation or active vegetation boundaries. Actually, he's asking this one. And if it is one of the two, is the other option also possible?
So yeah, in fact, the two are probably rather indistinguishable, but if they are, the difference comes from the use case. What do you want to do? In a sense, field delineation. So it's kind of a land use versus land cover question. So the field delineation that we can do from the surface, so from observing what is happening, closely follows what is happening with the surface itself. So with the vegetation, to some extent with the agricultural practices, right? So if half of the field is being mowed at some point, of course, the difference between the two halves of the field will be much strongly present in the model itself, and probably we will have the delineation done on that, so the field would be split into two. Again, this plays the time window over which we are running the model, and then temporal merging plays a role into this. And I'm not really sure. So I think that tweaking this time window when you're doing the prediction, you could actually distinguish between the two, but insofar, at least in the, let's say, in the common agricultural policy field, you would want to see these differences. So you would want to see that half of the field has already been plowed or mowed or whatever, and the other one wasn't. So there is still a lot of work, let's say, in the common agricultural policy, once you have the field delineation, to really say what is one field and what are two fields. I'm not really sure, Ralph, if I've answered, but yeah, feel free to email us and we can continue the discussion.
I believe the next two questions will be for Davis. The first one is from Aster, and the question is, could we assess crop water productively for specific crop after we delineate the specific area?
I'm not entirely sure about this. So we haven't tried sort of this directly, although basically we are sort of active in the agricultural monitoring and area monitoring. So basically once you have this step, which is sort of assumed once you want to do any analysis on the actual parcel, you can then look at sort of aggregated statistics over your parcel to try to characterize what's going on. And we've done this sort of successfully then for bare soil mowing, sort of for different markers that can characterize the status of your parcel. And sort of if you can derive this sort of crop water from some index or sort of from the reflectances of your band, then I would say you can use these parcels again as a starting point then to compute statistics to develop sort of your algorithm for basically predicting this index or this variable.
In your experience, what are the challenges that still remain in field boundary delineation tasks using the Earth observation data, such as Sentinel-2 and others?
I can give a quick maybe summary of the challenges that we maybe faced. So definitely one is these limits on the spatial resolution of Sentinel-2 and sort of the existence of very small parcels, especially in Europe. So these, as mentioned, so using a different imaging data source with a better spatial resolution can definitely sort of solve partially this. We've also seen, as mentioned, sort of a different definition, or possibly you might be interested in different things. So to explain, you might be interested to get parcels, say, every month, so you can start tracking how your parcel is developing. Or you can be interested to get sort of an average parcel throughout your growing season. And definitely another thing that we've seen is sort of the variability that you can find sort of across large regions. Sort of our aim is to do this large scale. So you find a lot of differences, for instance, in the labels, how different countries or paying agencies sort of define their parcels, and how they use them. So these are all sort of challenges that require very specific tailoring or sort of customization of your model. And another variability, for instance, could be that on the same sort of land, you could have multiple crops during one season, and they could even use sort of different geometries, right? So once they could be split sort of vertically, once horizontally, sort of to then change. So these are all sort of variabilities that make this task difficult.
Did we apply any stratification based on parcels dimensions to balance the different types of parcels?
No, by default, we don't do that. So the only similar thing that we do is we impose a restriction on the sampling. So each sample has to contain, so at least 40% of the sample needs to be agricultural land where the reference data is available. But we don't do any stratification in that manner, no. It seems that from our experience in our use case, it seems that this wasn't apparently needed, but for sure it's one of the possible improvements later on.
Nate, can you also tell us more about the accuracy of the model?
I think this was already kind of mentioned by Davis in one of the previous comments, but I would refer you to our blog post on Medium. There's some numbers about the accuracy that we achieved, and also the comparison of different architectures and the accuracies of those.
Is there a possibility of connection between neighboring farms if you are using any algorithm in post-processing to disconnect them?
I will try and answer this. So again, I think this refers to the training data that you use. So the issue might be, or the issue that we've encountered, is that in your training data, actually these parcels are not separated. So they could be given for the entire sort of parcels belonging to the same farmer. And this doesn't reflect actually what's on the ground. So you would have different parcels or sub-parcels where you actually see physical boundaries, but you would have a single geometry that sort of describes all of them. So this is an issue then when you actually want to delineate the single sub-parcels. So you'd have to pay attention to this when you create your training data. Or at least this is what we wanted. And we try to make sure that you have basically a one-to-one correspondence between your vector, your reference data, and sort of the parcel with the physical boundaries on the ground. So if you do this, actually, then the predictions should give you very separate sort of parcels, even for the same farmer. If instead you don't want this, then this task is more challenging. If instead you wanted like sort of a single geometry for multiple parcels belonging to the same farmer, this is much harder, because on one hand you tell the model to find boundaries, and on the other hand you say maybe not for this farmer. So this won't work very well. So I would say basically the training data would reflect how you would deal with this.
And since we already exceeded our time for today's webinar, we will take just the last question from Mehmet. He is asking if we plan to provide free membership to Sentinel Hubs for students and researchers. So we already have pricely available exploration package, but you can also apply for freely available accounts provided by ESA. So Nate, if you go just back to one slide, maybe we can attend also this one. Here you have also more information and links for free trial accounts. If you don't have one yet, you can create one. And ESA-sponsored accounts are providing also access to high-resolution commercial data. So maybe also something interesting for you. You can always get in touch with us. You can send us an email. Feel free to use GitHub or forum. And I would like to invite you to stay tuned, follow our social media for our future webinars. And thank you all for attending. And we wish you a nice Thursday.